So today we are finishing our homework with the Pinocchio snark construction. And what did we do exactly? Let's start by a review with a thicker pen. So we have a construction last time that is somehow, it's clearly, I use this word in the classical mathematician sense, it is clearly existentially sound. What does that mean? Well, what did we do? We took some statement and we translated it to an arithmetic circuit. And once we had an arithmetic circuit, we could encode a satisfying assignment into a set of polynomials representing constraints. So the constraints being, for example, if you have an addition gate, then of course the output has to be the sum of the inputs and so on. We converted all of these constraints into polynomials. And then what exactly did we do to prove our statement? We showed that we could prove the null, we showed that we knew some weighted sum of these polynomials satisfying all constraints simultaneously, which means we know a satisfying assignment to the circuit. Okay, prove knowledge of a weighted sum satisfying all constraints. And I say clearly existentially sound, glossing over the details because this is quite a complicated construction. If we were to really prove this, this would take a long time. You can read the original paper for a detailed proof. But the argument that we sketched out last time somehow makes it intuitively clear that if you can produce the field elements that satisfy all these conditions that the verifier checks, then unless you got extremely lucky, you must have known polynomials that satisfy all these constraints. Why? I mentioned last time there was a result that I did not write down the name of. The basic reason that we claim that this is existentially sound is the Schwarz-Zippel lemma. And this essentially tells you that if you have a polynomial, if you want a polynomial to be, I am choking slightly. Give me a second to think about this. So the goal is, right, that you want to determine whether a polynomial has a root at some particular point. And it says that if you choose a random polynomial, the probability that it has a point, that it has a zero at some random point is very, very small. So it's extremely unlikely that you can guess a polynomial that satisfies all the conditions that the verifier checks. Okay, so this is the key idea. If you check a detailed proof, we rely on this to show that the prover cannot, except with very, very small probability, guess these polynomials that it is evaluating. Okay, so what did we leave out last time? We didn't talk about zero knowledge. In fact, the proof is not zero knowledge, as I presented it last time. We can argue that quite easily. I left the question of what exactly is this homomorphic commitment? How do I construct a homomorphic commitment? I left that open. And also non-interactivity, right? Because the version of the snark that I gave is in fact interactive, which we don't want. Okay. So why is it not zero knowledge? Because I moved to the second board. that we have this as a review. Okay. Why is this not zero knowledge? So the prover, remember, has polynomials L, R, O, and H. And the verifier, through the course of the proof, obtains commitments to L evaluated at some secret point S, R evaluated at some secret point S, etc. So these commitments contain non-zero information. Why? Well, the commitments themselves are deterministic. Once you fix an S and a polynomial, you know it's a one-to-one map, right? So what could the verifier do? The verifier could take some other satisfying assignment recall that these polynomials L, etc., are of the form set a weighted sum that's of the form CI Li for I equals 1 to M, and the same for R, O, and H, where the Li's, Ri's are public knowledge, the CI's are the secret knowledge that we're proving that we know. So the verifier could take some other satisfying assignment, right? So some other things, C1 ... CM prime, and just compute the resulting commitments. So how does this leak knowledge? Well, the verifier now, once they do this, they know for sure if the commitments are not the same thing, then the verifier knows that the prover's satisfying assignment is different to the one the verifier has, right? So we learn something through the proof, namely, we can take any polynomial number of such assignments and exclude them as the possibility, as what the prover possibly has. That's not zero knowledge, right? Maybe you could argue it's not very useful knowledge, sure, but it's certainly not zero knowledge. Okay. Do you agree with me there, Dan?
Just because it's polynomial, right?
What do you mean? Yeah. So if you could compute a non-polynomial number, then you could compute all of them, right? And then you would learn the exact satisfying assignment. But we assume that the verifier is computationally bounded here.
Yeah. Okay. Yeah, I follow you.
Yeah. Okay, so how are we going to fix this? The idea is to just add some randomness to our polynomials in such a way that it doesn't change the soundness property. Okay, so what exactly are we proving? At the end of the day, we want to prove that the target polynomial t, which encodes the circuit, t divides LR minus O. In other words, that LR minus O equals TH. Okay, so LR and O are the left, right, and output constraints respectively, and H is just the division, the quotient when we divide by the target polynomial. So what could we do to add some randomness? Well, if we add a multiple of t to all of L, R, and O, then we still have that t divides the result, right? So we can set L bar to be L plus delta 1 times t. We can set R bar to be R plus delta 2 times t. We can set O bar to be O plus delta 3 of t, where the deltas are just uniformly random field elements. Not uniformly random, not zero field elements. Wouldn't be very useful if we're adding 0 to our polynomial. Then, of course, we still have t divides L bar times R bar minus O bar. So we still have to figure out what our h is. Um, we can just do the division, right? I'll spare you the details. What we need is that h bar is h plus delta 2 L plus delta 1 R plus delta 1 delta 2 T minus delta 3. Then we have L R minus O all barred equals T times H bar. And the proof is still accepted.
That's so neat.
You reckon?
I don't know. It's just you're working in the quotient ring, right? Somehow it's very satisfying.
Yeah, exactly. Right. To unpack that comment a little bit, we're sort of saying, okay, but if you shift each of these polynomials by a constant factor of t, then they're equivalent somehow. They're still a satisfying assignment. So if you do that quotient, then, well, I mean, they're in the same equivalence class, no problem, right? I didn't look at it that way. That's an interesting perspective. What I like about it is that this is like dead simple, right? There's nothing fancy. There's no complicated math happening here. Somehow we're doing the obvious thing, but it's only obvious because I said you could do it, right? All of these tricks with polynomials have that vibe. They're dead obvious, but how would you even think of them? I don't know.
Yeah, you have to internalize that you're working with functions on the set of satisfying assignments,
Right,
which is that quotient ring. So it's
exactly.
This is an awesome. If I ever teach a public course on algebraic geometry or need some example, I'll try and see if I can work this in.
I think it's a really cute way to sort of see how you can use these tricks somehow in a really, well, I don't know. In my mind, this is a very concrete application. Maybe some people would disagree, but to me, this is pretty concrete. Okay, so where are we? Well, we're still proving the same statement, right? We're proving knowledge of a satisfying assignment, but we added a uniformly random multiple of some constant, which means that L bar contains no information about L, or more specifically, L bar of S looks uniformly random. Okay, and it's the same old trick that we use everywhere in crypto. You add a uniformly random value to anything, you end up with something uniformly random, assuming it's independently drawn, right? Same trick we use everywhere in crypto, looks uniformly random. Intuitively, this allows you to produce a zero knowledge simulator, right? And why do I say that? Whenever you have something that looks random, the idea is the simulator can just choose it at random and then work backwards to construct stuff that makes it consistent, right? Remember that zero knowledge is defined as the verifier could simulate the proof. How does this verifier do this simulation? By choosing the answer that it needs to get and working backwards. And the reason that doesn't mean that you can cheat the proof is because the prover had to commit to something in the beginning, but the verifier simulating the proof doesn't have to commit in the beginning. Okay, so it's the exact same idea. I'm not going to show you the simulator for the same reason that I'm not showing a proof that it's existentially sound. This would take pages of careful algebraic stuff that is not especially interesting. Hopefully you believe me that because these commitments look uniformly random, we could produce such a simulator.
I'm a little worried about this last
statement. I just
statement.
claim without proof that it works out. Huh? What was that, Dan?
I'm a little worried about this last statement. I mean, I guess I believe that for any the one at the bottom, that L bar S looks uniformly random. So for any given S, maybe that's true, but if you, as a function, L bar is not uniformly random.
Right. So a key part of the argument is that we fix S at the beginning. The verifier chooses S and never reveals its value. So if you evaluate, so from the prover's side, you're evaluating the polynomial at a random point plus a uniformly random multiple of some other polynomial evaluated at that point. And we can lean on the Schwarz-Zippel lemma again to argue that the probability that this like works out in such a way to screw us is very, very small.
Okay, yeah, that's neat.
Yeah. I would recommend reading the paper if you have like a couple hours on your hands. But it really is. I mean, it's a lot of technical stuff that, in my opinion, is not very deep. There's not a lot of concept. It's just really checking that everything works, right? So I don't think it's useful for me to elaborate in detail.
No, I think I'd buy it.
Okay, so that's zero knowledge, and it really is that easy, right? This is sort of an interesting pattern in this kind of zero knowledge proof, where you take some proof that is clearly sound and you just add a bit of randomness to it. And if you do it in the right way, you can produce zero knowledge out of it. So now I have to sort out this homomorphic commitment deal. Okay, so what was a homomorphic commitment? We have efficiently computable. I mean, this is just a standard thing in computer science, right? It's not very useful if we have a function that is not computable or not efficiently computable. Right, so function com, it goes from our field to some commitment space. I'm going to use calligraphic C. Doesn't really matter what this space is, such that it's a ring homomorphism in some sense. And the reason I'm weasel wording here is because what we will end up with is something that is not quite a ring homomorphism, but it has some similar properties. Okay, and what do I mean by that? So if I know, given a commitment of X and the commitment of Y, we can compute brackets efficiently. I'm not going to write the word efficiently everywhere, but when I say we can compute, I mean we can do it efficiently. We can compute a commitment to the product and a commitment to the sum. Okay, so I'm not asserting the existence of a ring structure in C, but I am asserting that you can sort of evaluate it homomorphically in some way in this sense. Okay, but we also require that pre-images are hard to compute. Okay, so if you have some commitment, intuitively it should be hard to reverse it. The commitment hides the value. Okay, so this condition is easy to almost meet, okay, using something called a Pedersen commitment. And this is a very simple algorithm. We let our commitment space be a cyclic group, palm, cyclic group of some prime order. And we fix some generator G, and we define that the Pedersen commitment of X is G to the power of X. Okay, and if discrete logarithms are hard to compute in the group, of course, by definition, finding pre-images is hard to do. And we also have the obvious, air quotes, obvious homomorphic property that a commitment to X plus Y is a commitment to X times a commitment to Y, just using the exponential laws. Right, that's going to be G to the X plus Y. Easy, right? We can easily do additive homomorphicity. Multiplicative homomorphicity is much harder. There's a technique using the ideas behind something called the Paillet crypto system that you can do multiplicative homomorphism, but then you can't do an additive homomorphism. So we need some way to do both multiplicative and additive homomorphisms. And here's one way that we can do it. Okay. So we need some similarly hard one-way function that has a neat structure to it. And when a cryptographer wants some neat structure, what do? They reach for elliptic curves. So let's begin. We take G1 to be an elliptic curve over our field. An elliptic curve. If you don't know what elliptic curves are, then don't worry, we're going to use them as a black box. All you need to know is that these things are going to have cyclic group structure. Okay, so take an elliptic curve of prime order R, which is not equal to the field order, such that the least down at some point is going to go, oh, I know what this is. The smallest number such that R divides the field order to the power of K minus 1 is big enough, whatever that means. Okay. Details I'll write in blue. The embedding degree, as that is called, at least 6. And in practice, we usually use 12. Why? We think it is conjectured that an embedding degree that's at least this high means discrete logarithms are hard in the group. There's sort of some heuristic arguments for this. I can't really give you a good mathematical argument for it, but we think that if this condition is satisfied, then we have a group where discrete logarithms are hard to compute, which is nice because it's sort of, if you just take some random cyclic group, it's sort of hard to decide whether discrete logarithms are going to be hard. So here's a nice big family of cyclic groups where we think discrete logs are going to be hard. Yeah, in practice, usually you want an embedding degree of 12. Okay, so what does this give us? We have some group. I call it G1, so it's probably not going to shock you that we're going to have some other groups appearing. Notice that since I asked that R divides P to the K minus 1, then if I look at the field with P to the K elements, the group of units has a subgroup of order R. Okay, so order R. So this thing here has P to the K minus 1 elements because it's everything except 0, and R divides it, so Lagrange's theorem, right? We've got some subgroup of order R, and we're going to call this group GT. YT, it stands for torsion. If that doesn't make sense to you, just don't worry about it. We don't need the details. And now we're going to consider the same elliptic curve from G1, but over this group FP to the K, over this field FP to the K. Okay, so the elliptic curve now has a bunch more points in it. Same elliptic curve from G1, E over FP to the K. Of course, it's going to have, since FP is a subfield of FP to the K, it's also got G1 as a subgroup. But it also has some other subgroup of order R. Actually, it has R minus 1 other subgroups of order R. And we call this G2. Okay, so we have two subgroups of order R, two subgroups of this elliptic field, of this elliptic curve rather, of order R. And we also have a subgroup of the group of units of order R. Okay. And we're going to fix some generators. Oops, R is prime, so they have generators. A in G1, B in G2, and use the Tate pairing. So this is where some fairly deep number theory rears its head in crypto. I certainly don't understand the Tate pairing in great detail, but I know what properties it has. So as a cryptographer, I'm happy with that.
Yeah,
I started trying to read about this and I got very quickly down a deep rabbit hole. I went, okay, maybe this is the problem for future me. So the picture is we just have a bunch of groups that have these intricate relationships that allow us to define a function that is going to do, that is going to have the properties that we need. The function is tate from G1 times G2 to GT. And the properties that it has that we're really interested in is that, my notes are inconsistent. I changed notation halfway through. Yeah, that makes more sense. So that we don't get confused by our letters, I'm going to call the first generator, hello? I'm going to call the first generator A1, the second generator A2, A1 for G1, A2 for G2. And we need that when we apply this function to the generators, we get a generator of the codomain. And we'll call this generator small g. Note, elliptic curve points get capital letters. This thing in GT is in a group of units. So it's a number in some sense. So we use a lowercase letter. That's the convention I'm following. And for any x and y in field of order R, we have the tate of x times a1 and y times a2 equals g to the xy. Okay, so in other words, remember that these groups are of order R, so the exponents are in the field of with R elements, and the Tate pairing has this nice property, this multiplicative homomorphism property on the generators. Fantastic. This, as we will see, is enough for us to produce something that is almost a homomorphic commitment, close enough that we can actually do it. The Pedersen commitment is not close enough, but we can use the Tate pairing to produce something that is close enough.
I would never have thought this was relevant to cryptography. Yeah, I would have never
yeah. So the point is that the Tate pairing is believed to be hard to invert, right?
Uh-huh. Yeah, I wouldn't have ever thought about that.
And once you have something that's believed to be hard to invert, cryptographers often say,
we'll
hello.
Find it.
Yes, I'm interested. Yes. So what's the idea? Very, very briefly of the Tate pairing, so that this is maybe slightly less mysterious. Let's take some point P in G1, so it's an elliptic curve point. We can define a function fp from G1 to our field that in some arcane sense has a zero of multiplicity R at P and no other zeros. Okay, so like how a polynomial can have roots of various multiplicities, we can, in some arcane sense, define a function associated to a point that has a zero of multiplicity R there and no other zeros. Then the Tate pairing of 2 points P and Q is this function evaluated at Q to the power of p to the k minus 1 divided by r. Why does this work? You can read a ton of theory if you like. I just present this so that you know I'm not magicking something out of the ether, right? This is a thing that can in principle be understood. Okay. So now I'm going to argue that we can in fact produce something commitment out of this. So let's define C1 as a function fp to G1. So C1 is going to take a field element, which is the domain of our commitment, and give us an element of G1. What's a sensible way to do that? Well, obviously, it's just x times the generator, right? That's an obvious way to do that. Fp to G2, again, x times the generator. Ct from Fp to Gt. The Gt is made of field elements. So this is going to be G to the power of x. Okay. These are all homomorphisms. You can check if you like. In particular, because they're group homomorphisms, we can compute a commitment to x plus y easily, right? Commitment of x times y is going to be a commitment of x plus y. So we've got the additive homomorphism inherited from the Peterson style commitment, where you just raise the generator to some power. And now we need to produce a multiplicative homomorphism. So why did I say it's almost a commitment? Because we have these three different groups, right? If I evaluate C1 on something, I get a G1. If I evaluate C2 on something, I get a G2. How can I add a G1 to a G2? Not completely clear, but if I know C1 of x and C2 of y, I can compute Ct of x times y. That's going to be g to the xy, which is the Tate pairing x times a1, y times a2. That's by that second property on the last board. And of course, by definition, this is Tate of c1 of x, c2 of y. Okay, so I can compute a commitment in GT given a commitment in G1 and G2 that is multiplicatively homomorphic. It doesn't meet the definition because we have three different groups here, but it's close enough. Why is it close enough? Oh, sure. If we have an indexed family, C1, Ci, for I is between 0 and n, and C2, Ci, s to the power of I, rather. Zero is less than or equal to I is less than or equal to m. We can compute the weighted sum Ct sum over I Ci s to the power of I. In other words, we can compute a commitment to our polynomial evaluated at point S if we have commitments to our weights and commitments to powers of the secret value. And that's how we did the blind evaluation of the polynomial, right? We gave the verifier gives the prover commitments to the secret raised to various powers, and the prover uses that together with its its assignment commitments to evaluate the polynomial at that point. So even though this is not a homomorphic commitment in the strict sense because the types don't work out, it's good enough for our purposes. We can make the types work out. So the idea is that we have some strange arcane bit of number theory that, if we massage it a bit, allows us to compute a multiplicative homomorphism in just exactly the way that we need. And if you've forgotten how the homomorphism works, I'm about to remind you when I argue non-interactivity. Okay, so the last thing that I was missing is how to make the proof non-interactive. Maybe you're thinking, can we do the Fiat-Shamir transformation? That's where you hash the commitment, that's where you hash the statement, the commitment, a bunch of other things together, and that gives you your challenge to make it non-interactive. It can make any Sigma protocol non-interactive, but we don't have a Sigma protocol. We didn't prove the required properties, but we do have another interesting property. In particular, the verifier sends the first message. In the proofs we've looked at so far, the prover sends the first message, a commitment. But this time the verifier is sending the first message. So we can use this to our advantage. So let's remember how blind evaluation works. This is the core of the zero knowledge proof. The setup is, as public information, we have some prime and some degree. To avoid confusion, I'm going to use Alice as the prover because we need P later. So Alice knows some value A in the field that we're going to use and some polynomial over the field. And that polynomial is going to be C0 plus C1 x plus dot 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 plus CD x to the D. Okay, and Alice is going to blindly evaluate the polynomial at some point. And what does Bob do? Bob, the verifier, has some secret value S that is drawn uniformly at random, some other secret value alpha drawn uniformly at random from the units. Okay. The first step is that Bob sends commitments C1 of 1, C1 of S, dot, 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 up to C1 of S to the power of D, C2 of alpha, C2 of alpha S, dot, 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 C2 alpha S to the D. Alice computes C1 of P of S. How? Using the additive homomorphism. That's C1 of C0 plus the sum from I equals 1 to C1 of S. Sum from I equals 1 to C D. The commitment S to the D. Okay, this expression is by the additive homomorphism. That's C1 of C1. I chose those names poorly. That's C1. That's a commitment to C1 of S. There we go. And that's a commitment.
It's curly.
CD.
It's okay.
It's a commitment to CD times S to the power of D. Okay. So I read it out as a sum just to show you that yes, Alice actually can compute this. And in a similar manner, a commitment to alpha P of S and sends them to Bob. Now what Bob has to do is check that the Tate pairing C1 P of S C2 alpha equals the Tate pairing. C1 of 1, C2 alpha times P of S. Why? This is CT of P of S times alpha. This is CT of 1 times alpha P of S. Okay, so they should be equal if Ellis is being honest. And since Ellis is proved knowledge in this way of some coefficient and polynomial, that means that Ellis must have really evaluated a polynomial, which is enough, right? So the confusing thing here is Ellis somehow controls this value A, which I didn't use. My notes must have gotten confused somewhere. The confusing thing is Ellis controls the polynomial, right? So all that you're proving here is that Ellis really has evaluated some polynomial at some point. But this is all that we needed to prove in the end, because it was proving knowledge of a polynomial with these coefficients matching up in the right way. Okay, so what did we need in order to do this proof? What did Ellis need in order to do this proof? Ellis needed somehow to already have these values, right? Ellis needed to already have commitments to 1s up to s to the d and alpha s to the d. So if we could somehow make these values public knowledge without anybody knowing alpha or s, then we could do the proof non-interactively, right? If these are public knowledge and nobody knows the secrets, then Ellis can compute a convincing proof without interacting with anybody. So it'd be nice if we could do that. The good news is we can do that. This is called the common reference string model. Oops. And the idea of the common reference string model is we just assume public knowledge of a string right? A string being just binary values, it could encode anything you want, right? We just assume public knowledge of some string generated in a particular way. From some secrets. So in the CRS model, we just assume that this is the case. And then it's easy to see how the protocol becomes non-interactive, right? The prover only has one step. They do their computation, publish the results, and now anyone can check that the required equation holds, and it's convincing because the value is a secret. That's it, done, QED.
Wait, what?
Thank you, I was waiting for you to say that. Okay, what? What? Why the hell can we assume that? That doesn't make any sense, right? So in particular, what we assumed was that we had as public knowledge commitments to SI for I is between 0 and some upper bound M, and commitments to alpha times S to the I, where alpha and S are known to nobody. We just assume that this is the case. Why the hell can we do that? Well, the good news is there's something called verifiable secret sharing. And the idea behind verifiable secret sharing is we have a bunch of parties who are each going to pick some private value, let's call this S1, S2, S3, for example. They each choose some random value secretly, and we define S to be S1 plus S2 plus S3. And these parties are going to execute some interactive protocol. And at the end of the day, they give us a commitment to this sum S1 plus S2 plus S3 in such a way that nobody ever learns any values except their own. Okay, so this is a multi-party computation, right? We have each of these parties, they have their own share of the secret value, and by executing the protocol, they never learn anyone else's value. And yet they can verify that the parties really did choose some fixed random secret to produce this commitment. So using this, we can do it. We can jointly compute such commitments. The heart of it is that it's a homomorphism, right? Because it's a homomorphism, you can compute your commitment locally and then add them all up. Such that S remains secret as long as at least one participant is honest.
Not following the at least one part.
Yeah, so let's think about it. How could this protocol go wrong? Well, let's say, for example, that one party, let's say that all of the participants are working together to make it look like they're choosing random values, but actually they're not. What could happen? Well, one thing that could happen is that S1, S2, and S3 could be chosen in such a way that they happen to add up to 0. If they add up to 0, then you have commitments to 0. But to any observer, it'll look like the commitments were indeed random values, right? Because, I mean, these are just values that happen to add up to 0. And yet the protocol is completely broken because the participants all know that the final value is 0. Why does it work as long as at least one of the participants really is randomly choosing SI? It's the same argument that we used before, right? As long as at least one of the values in this sum is uniformly random, then the result is uniformly random. So this is why the common reference string model is considered meaningful, right? You really can do this as long as you have a group of people where you can trust at least one of them to be honest, or a different perspective, as long as you can trust that not all of them will agree to work together, right? So maybe it's that they're all behaving dishonestly in some sense, but there's no situation where they are all working together to reconstruct the secret. Okay, you could, for example, imagine political parties, right? Political parties have a pretty strong incentive to not collaborate with their opposition. At least in a healthy democracy, they have a strong incentive to not collaborate with their opposition. So you might choose representatives from major parties under the understanding that because their incentives are misaligned, they won't want to all work together. And this is actually what Zcash did. So Zcash it's a blockchain that has a focus on privacy. So they did a lot of work around anonymous transactions, and they use this SNARK construction. Actually, they use more modern SNARK constructions now, but they use the same idea to do this, right? So the idea is, I'm going to prove that my transaction was legitimate, was allowed, and wasn't a double spend, all in zero knowledge so that you never learn who I sent it to. And in 2016, they took 6 people spread around the world with hardware that they were told to go to a random computer shop and buy a random computer from the random computer shop to try to eliminate the chance that all of the computers were compromised at the same time. And they did an online protocol using this verifiable secret sharing to compute a common reference string for the blockchain's SNARKs. And one of the people I was surprised to find out is Edward Snowden, which I think is kind of cool. They chose some other experts. They chose some security experts and so on. So the idea being probably not all of these people are going to collaborate, probably. Okay. So that's it. What did we do? We have a non-interactive. We have a zero knowledge, non-interactive, argument of knowledge, argument because there's a non-zero soundness error, negligible at non-zero, with a proof size well, how much data does the prover now need to publish in order to produce a convincing proof? It's a grand total of 5 elements of G1. That's 5 evaluations. That's 4 evaluation. That's 1 evaluation of each polynomial plus an extra value. And 4 elements of G2. That's 1 of each polynomial. That's it. That's the proof size. And it's true. And the proof is this size, regardless of any parameters except, of course, the size of the group, P and R. That's it. So the only thing that affects the size of the proof is your security margin. Because we're publishing a single group element 9 times. That's it. It is deeply shocking that this is possible. Okay, no matter how complicated the thing you're trying to prove is, you still have a proof that it's just 9 group elements. So with a lot of clever tricks, if you target your usual security level, 128 bits, the proof size is 288 bytes. No matter how complicated the circuit is. Proof computation. The way that I presented it, it's going to take it's not this efficient, but you can be smart about it. It's linear time in circuit depth. And verifying is linear time in the input and output sizes, so the number of input and output. And concretely, this takes about 10 milliseconds to verify a proof. Again, no matter how big the circuit is, modulo like reasonable assumptions about what you might actually want to prove in practice. Yeah, this is one of my favorite results in all of mathematics, actually, that this is possible. And you can extend it to any NP statement. You probably don't want to, but you could. So yeah, you can do this. That's it, constant size, linear proof computation, linear verification computation. I'm hiding something here. What do you think I'm hiding, Dan?
I don't know. It's magic.
I said that verifying takes 10 milliseconds. Proving takes about 10 minutes.
I see.
So this is the last little detail about SNARKS. Proving is extremely expensive. The good news is more recent constructions like Plonk can do like order of 10 seconds, which is still pretty expensive, but it's still an important practical concern. Okay, that's it. if you want to look at more complex constructions, Plonk is a good one to look at. There's a lot of also breadcrumbs that you can follow there. I think I'm going to wrap up at least this season of crypto here with this astonishing result that we can prove any NP statement in constant space and linear time.
Yeah, that was great. I thoroughly enjoyed that. I understand why you went into crypto.
Yeah, right. We can do the impossible here.
Yeah.
All right, I've got to run.
Yeah, thanks a lot.
But I can take questions in Discord and so on.
Yeah.
All right, have a good one, Dan.
Yeah, see you, Eleanor.